Some black holes weigh more than 1 billion suns, they're the heavyweights of the universe. Picture a tiny seed that, over billions of years, turns into a cosmic skyscraper at the center of a galaxy. That's a supermassive black hole. Instead of jargon, think snowballing. As it rolls through space it gathers gas and stars, growing bigger and stirring up its neighborhood like a giant mixing spoon. Sometimes it glows like a cosmic lighthouse, other times it gorges quietly. Imagine a picky eater who suddenly binges on a whole buffet. Watch on to see simple animations and everyday comparisons that show how these giants are born, how they feed, and why they help shape entire galaxies, and by the end you'll have a few surprising facts to drop at your next dinner party. Science bonus: you'll sound smart without sounding like a robot. A universe of monsters. What are supermassive black holes? At the center of almost every large galaxy sits a supermassive black hole, an object millions to billions of times more massive than the Sun, whose gravity governs the motion of nearby stars and gas. These monsters are not ordinary holes, they are regions where gravity is so strong that, past a certain boundary called the event horizon, nothing can escape, not even light. The event horizon acts like a one-way gate: you can go in, but you cannot come back out, and that simple fact is why they look dark against the bright background of space. Around many of these black holes a spinning disk of gas and dust forms as material spirals inward. This accretion disk gets squeezed and heated, glowing brightly in visible light, 10th rays, and radio waves, bright enough to outshine the whole galaxy in some cases. Picture a kitchen sink whirlpool that gets hotter and brighter the faster the water spins, except the whirlpool can blast narrow, powerful jets of particles out from its poles that travel for enormous distances. Those jets are like cosmic blowtorches, and they can shape the galaxy's surroundings by pushing gas away or lighting up space for millions of light years. Astronomers spot supermassive black holes in a few clever ways. They watch the motions of stars and gas. If stars circle a compact, invisible object very quickly, that points to a massive, compact source of gravity. They also detect the bright light from accretion disks and the specific fingerprints of 10th rays and radio waves coming from near the event horizon. In addition, very long baseline radio telescopes can combine their views to make a detailed image of the shadow the black hole casts against the glowing disk, revealing the outline of the event horizon itself. Recently, ripples in spacetime called gravitational waves have also given clues when very large black holes merge, though those signals come from the final, dramatic moments. These black holes influence their galaxies in practical ways. By swallowing or heating gas, they can slow down new star formation, acting like a bully at the gas fountain, or sometimes they stir things up and trigger bursts of star birth elsewhere. They are not greedy eaters that vacuum up everything. Feeding is intermittent, like a diner who only orders when tempted. The scale of their influence is enormous. A supermassive black hole's reach can determine whether a galaxy becomes a quiet ball of old stars or a lively, star-forming city. Explaining them without jargon makes them less mystical and more like parts of a complex engine that runs galaxies. Simple comparisons, whirlpools, drains, and kitchen blowtorches, help, but the real universe is stranger and more precise. Scientists keep refining how we measure their masses and watch how they interact with their surroundings, because understanding these giants helps explain why galaxies look the way they do today. And yes, they are dark, they are powerful, and they are much more fascinating than the monster under the bed idea. Fortunately, they're very far away and not interested in household snacks. Cosmic nursery, the seeds of black holes. Some black holes begin life as the leftovers of very massive stars that run out of fuel and collapse under their own weight. When a giant star dies, its core can fall inward and leave behind a compact object that has several to a few dozen times the mass of the Sun. These are the smallest seeds. In a crowded cosmic neighborhood, those small seeds can later merge with others or soak up gas and grow bigger, much like how a small snowball becomes an avalanche if it rolls down a hill collecting more snow. Astronomers have seen many of these stellar mass black holes through the ripples they make in space when they merge, which gives direct clues about how common these tiny seeds are. Another pathway makes much heavier baby black holes directly from big clouds of gas that never split into lots of little stars. Under the right conditions, when the gas is thick, calm enough not to fragment, and not full of heavy elements, a whole chunk can collapse straight into a black hole that starts life thousands to millions of times the sun's mass. Think of it like baking one giant loaf instead of many rolls. The result is a single, very large object. Observations of extremely bright galactic centers suggest that some early black holes must have been born relatively heavy, or else they had to grow extraordinarily fast, and that's why this direct route is taken seriously. Dense star clusters provide a third nursery. In cramped clusters, stars can collide and merge in a runaway chain reaction, forming a superbig star that then collapses into a much heavier seed. Picture a crowded dance floor where people keep bumping into each other until a few form a human pyramid that no longer fits through the door. Simulations show that when many massive stars sit close together, repeated collisions are likely, and the resulting massive object can make an intermediate mass black hole, heavier than stellar remnants but lighter than the ones born by direct collapse. What happens next depends on the neighborhood. Seeds that sit in gas-rich regions can feed steadily, swallowing surrounding material and growing into the monster black holes found at galaxy centers, while those in quieter regions may stay small for a long time. Galaxy collisions and mergers also help by bringing fresh gas and other black holes into the same place, accelerating growth through mergers and feeding. Current telescopes pick up signs of active feeding, bright light from gas heating as it falls in, so astronomers combine those observations with theoretical models to figure out which birth paths were most important. It's a bit like tracking startup companies. Some begin with a big investment, some grow slowly, and some get huge fast after a lucky merger. From pop third stars to heavy seeds, early pathways. The earliest stars burned from gas made almost entirely of hydrogen and helium, and because there were no heavier elements to help the gas cool, those first stars tended to be very large and short-lived. These primordial stars, often called pop third, short for population third, left behind compact remnants when they died, and some of those remnants were black holes. Think of a campfire where the biggest logs burn out fastest and leave hot coals. Those coals are the small seeds that can later spark larger fires, but not the kind you roast marshmallows on. Some black holes began small, as the leftovers from single massive stars. Others might have formed much larger to begin with, through a process where a vast cloud of gas collapsed almost all at once into a heavy seed instead of first breaking up into many smaller stars. Picture a neighborhood. One path builds many little houses one by one, and another path puts up a skyscraper by pouring one enormous foundation. Both lead to buildings, but the skyline looks very different. How the gas behaves decides which path is taken. Calm, dense gas with little stirring tends to fall inward smoothly, favoring a direct collapse into a big seed, while gas that fragments and makes many small stars produces stellar remnant black holes. Nearby bright sources can change the rules by bathing a gas cloud in light that keeps it hot and prevents it from breaking apart. It is a bit like trying to bake a cake. If the oven stays too hot in weird spots, the batter never sets into small cookies and instead becomes one big blob. Growth after birth follows two main strategies: feeding and combining. Feeding means gas still nearby spirals in and falls onto the seed, making it heavier over time. Combining means two or more black holes meet and merge, which can quickly make a bigger object. Both processes are seen in simulations and hinted at in observations. Telescopes that look for bright flickers of high-energy light can spot the feeding, while ripples in spacetime, yes, gravitational waves, reveal mergers. Together they give astronomers clues about which seeds were present. Like watching a city grow by new construction and corporate mergers, astronomers piece together the history from available signs. Realistic studies now favor a mixed picture. Small seeds from dying massive stars and heavy seeds from direct collapse events probably both happened, and their relative importance depends on local conditions in the early cosmos. Computer models act like urban planners testing different scenarios, while observations act like aerial photos confirming which neighborhoods actually formed. The result is a richer, more practical view. Supermassive black holes at the centers of galaxies likely had many childhoods, some starting as modest coals and others launched off a skyscraper foundation, and the universe, as it turns out, can be both patient and impatient when it comes to building giants. Direct collapse, forging giants without stars. Some giant clouds of gas in the early cosmos could collapse straight into enormous black holes without first assembling into normal stars. This route needs a few special conditions. The gas must stay hot enough to avoid breaking apart into many small clumps, it must lose enough spin or angular momentum so it can fall inward, and something nearby often has to shine strong ultraviolet light that stops the gas from cooling in the usual way. Cooling is what lets matter settle into lots of small stars. If that cooling is blocked, the whole cloud can fall inward as one big object. Think of it like a lump of cookie dough that never separates into individual cookies, and instead someone squashes it into a single giant cookie. To keep the gas from fragmenting, the usual coolant, molecular hydrogen, which is just pairs of hydrogen atoms that help gas chill, must be destroyed or suppressed. Strong ultraviolet light from a neighboring galaxy can do that by breaking the fragile bonds of those molecules. In everyday terms, it's like keeping a pot of stew hot by stirring it and adding heat nearby so it never cools enough to congeal into chunks. When molecular cooling is gone, atomic hydrogen becomes the main way the cloud radiates heat, and that tends to favor a smoother, more centralized collapse rather than many separate stars forming. Gas still has angular momentum, meaning it wants to spin instead of falling straight inward. Nature has clever ways to remove that spin, turbulence, gravitational torques from nearby structures, and cascading instability, sometimes nicknamed bars within bars, in the jargon. These act like a cosmic drain, letting material flow inward at high rates. Rapid inflow is crucial. If the center gets fed fast enough, the core can grow into a supermassive object, either a very massive star-like object that quickly collapses, or a massive seed black hole that continues to swallow gas. Either outcome leads to a black hole seed that can be thousands to millions of times the Sun's mass right from the start, which helps explain how some supermassive black holes appear so large so early. Computer models and telescope searches are the detectives on this case. Simulations show the rare conditions that lead to direct collapse and trace how a smooth, dense cloud could avoid fragmentation and feed a central object. Observationally, astronomers look for compact, bright sources with little sign of heavy elements, because metals come from earlier generations of stars, and for strong ultraviolet signatures that indicate the molecular coolant was being destroyed. Finding a clear example is hard, like spotting a specific fish in a vast ocean, but candidate regions and subtle clues keep the idea plausible. This pathway is rare, and rarity is part of the story. Suitable environments likely pop up only in special neighborhoods where a star-forming neighbor provides the right kind of radiation and the gas reservoir is large and calm enough to collapse cohesively. In plain language, the cosmic conditions have to be just so. Think of assembling a complicated piece of IKEA furniture without the instructions, and somehow ending up with the perfect table. The uniqueness explains why not every galaxy hosts an enormous black hole from birth, while still giving us a neat explanation for the biggest black holes that seem to have grown very quickly. Stellar collisions and dense clusters, alternative birthplaces. Some very large black holes may begin their lives in places where stars are packed so tightly they practically bump into each other. Astronomers point to crowded star groups, like the dense clusters near galaxy centers and the tightly packed star balls that form in bursts, as likely spots where collisions can happen often enough to matter. Observations of bright 10th-ray sources and the gravitational ripples picked up by detectors support the idea that collisions and mergers are happening out there, even if we cannot watch a single collision in real time. These clues, along with computer models, make the collision route a realistic alternative to the simpler, one star collapses on its own story. When heavy stars gather toward the center of a cluster, they raise the odds of hitting each other. This gathering is called mass segregation, and it works a bit like shoppers at a busy market. The big, slow carts tend to end up near the center of an aisle while smaller, nimbler shoppers dart around them. Another helpful concept is dynamical friction, which you can picture as the sticky feeling when you try to move through a crowded subway car. Big stars get slowed by the swarm of smaller ones and sink inward. In that cramped central region, stars can physically collide or form tight pairs that later merge. If enough mergers happen quickly, a single star can grow unusually large by eating neighbors in a runaway process, much like a snowball rolling downhill and collecting more snow until it becomes enormous. Runaway growth doesn't stop with a single big star. That heavyweight can collapse into a substantial black hole, and then more merging can follow. Some of these black holes can pair up and merge, producing even heftier black holes over time. Think of it like small companies merging into medium ones, then those joining to form a giant conglomerate. In dense clusters, close interactions can also eject some members, so the population changes like a chaotic business district where some shops close and others expand. Computer simulations show chains of such mergers can build objects that bridge the gap between regular stellar black holes and the very large beasts astronomers call intermediate mass black holes, which might then seed even larger systems under the right circumstances. What do observers look for if this is happening? They search for unusually bright 10th-ray points, signs of fast-moving stars near a hidden massive object, and the gravitational wave signatures of black holes colliding. Real-life examples help. Spotting a traffic jam at a busy intersection tells you where accidents are more likely. Similarly, finding a tight knot of stars suggests a higher chance of collisions. There are still open questions: how often clusters reach the exact conditions needed, and how many of those seeds survive long enough to grow large, but the collision pathway remains a lively and plausible story. It adds a colorful twist to how the universe builds its largest monsters: chaotic crowds, a bit of gravitational stickiness, and a few runaway mergers, nature's version of extreme crowd surfing. Feeding frenzy, accretion disks and growth. Supermassive black holes grow mostly by pulling in gas and dust that swirl around them in a flattened, spinning structure called an accretion disk. The disk forms because the incoming material carries angular momentum, which is why it doesn't fall straight in. Think of water circling a drain instead of plunging headfirst. Friction and turbulent motions inside the disk act like tiny brakes, letting the gas slowly lose that spin and creep inward. As it does, gravitational energy turns into heat and light, so the region near the black hole can glow incredibly brightly. A simple kitchen example helps. Stir a spoon through honey and watch how the honey heats slightly where it rubs. In a black hole disk, the rubbing is violent enough to make 10th rays and visible light. Radiation from the hot inner disk can push back on the inflowing gas, creating a natural speed limit on how fast the hole can grow. Astronomers call this the Eddington limit, and it represents the balance between the inward pull of gravity and the outward push of radiation. If the black hole tries to swallow matter faster than that balance allows, the light it produces can blow some material away, like a strong fan scattering leaves. Still, disks are clever. In certain messy, dense situations the flow can be puffed up and irregular, allowing temporary bursts of faster feeding. Think of a rushed all-you-can-eat buffet compared to steady dining. Magnetic fields threaded through the disk also matter a lot. They tangle and reconnect, acting like elastic bands that transfer angular momentum outward so gas can move inward, and sometimes they fling matter away in narrow, powerful jets that shoot out along the black hole's spin axis at speeds close to that of light. Picture combing wet hair. The comb, magnetic field, rearranges the strands, gas, letting some parts slip and other parts be flicked outward. Those jets and winds don't just look dramatic, they regulate growth by carrying off mass and energy, and they can influence the galaxy around the black hole by heating or pushing gas so stars form differently. Not every bit of material that reaches the inner disk ends up crossing the point of no return. Some of it gets heated and expelled in winds, some emits bright light and leaves, and some spirals over the edge. The efficiency of turning infalling matter into emitted light varies with how the disk is structured. A thin, orderly disk radiates very efficiently and shines like a lighthouse, while a thick, chaotic pile can trap radiation and let more mass sneak through. Observationally, this explains why some galactic centers blaze as quasars that outshine the rest of their galaxy, while others sit calmly, almost sleepy. Variations in the feeding rate also create flickers and flares in brightness that astronomers monitor like weather forecasters watching storms. Short, sudden increases in accretion light up the inner regions. Longer, steady inflows create persistent brightness. The whole process is messy, dramatic, and surprisingly similar to everyday flows of fluids and friction, except with more extreme temperatures and the occasional relativistic jet for flare. In the end, the growth of supermassive black holes is a balance of supply, brakes, and pushback, how much material arrives, how efficiently the disk lets it fall in, and how strongly light and magnetic forces keep things from being gobbled up too quickly. Quasars, the brightest beacons of black hole growth. Some of the brightest objects visible across the cosmos are powered by gas falling toward monster black holes, and that light tells us about how those black holes grow. When gas and dust spiral inward, they form a flattened, spinning disk that heats up as material rubs and collides, like air warming when you rub your hands together very fast. That glowing disk can outshine the combined light of all the stars in the surrounding galaxy, so a single nucleus becomes the most noticeable thing in the sky. One well-known example that helped astronomers realize how bright these objects can be is the quasar called 3C273, a source whose light stood out so strongly that it could be studied in great detail. Bright output is directly tied to feeding. The more material a black hole swallows per second, the more energy the infalling gas gives off before it disappears. There is a practical limit to how fast this can happen, because the light itself pushes back on the incoming gas. Think of it as trying to pour water against a strong breeze. At some point the breeze blows the drops away. Astronomers use that balance to estimate how fast black holes grow by comparing the light we see to the maximum steady rate allowed. The light also flickers and changes over days to months, which is a clue. Rapid changes mean the glowing region is compact, rather like judging the size of a distant bulb by how quickly it can be switched on and off. Spectra of these bright centers carry fingerprints that reveal physical conditions nearby. Gas close to the black hole moves at extremely high speeds and emits broad emission lines. Those broad shapes in a spectrum come from gas racing both toward and away from us, which spreads the light out in a way similar to how a police siren changes pitch as it speeds past. Meanwhile, light from the quasar travels through space and encounters clouds of gas between galaxies, leaving dark absorption lines along the way. This series of absorption features, often called the Lyman alpha forest, acts like a map of the gas the beam passed through. In simple terms, quasars are cosmic flashlights used to inspect the fog between islands of stars. Not all quasars look the same, and that variety tells another part of the growth story. Some have powerful, narrow jets that shoot material far outside the galaxy. These jets make the object loud at radio wavelengths and can be seen like cosmic fire hoses, streaming particles at near light speed. Other quasars are quieter in radio but still shine brilliantly in optical and 10th-ray light. If a jet happens to point nearly straight at Earth, the quasar appears even brighter and more variable, a bit like catching a car's headlight directly in your eyes. Those jets and also broad winds from the central region can push gas out of the galaxy, acting like a thermostat that can slow or even shut down star formation. In everyday terms, it's like removing the fuel from a camp stove so the flame has nothing more to burn. Using modern telescopes that watch radio waves, visible light, and 10th rays, astronomers piece together how quasars behave and how fast their black holes gain mass. Observations of quasar brightness, spectra, and jets together build a consistent picture. These luminous beacons are both signposts of active feeding and agents that influence their surroundings. They shine as bright lighthouses while quietly, or sometimes violently, changing the fate of their host galaxies, a mix of glamour and household-level drama on cosmic scales. Galaxy mergers, when black holes collide. When two galaxies come together, most of their stars sail past one another without hitting, but the very heavy centers, the supermassive black holes, are drawn toward the same new center and begin a slow, clumsy dance. Gravity acts like a crowd pushing against two slow-moving people at a party. As the black holes move through stars and gas, they lose momentum, a process astronomers call dynamical friction, which can be explained simply as the surrounding material tugging and slowing them down. Picture two ice skaters in a crowded rink gradually edging toward the middle while other skaters help nudge them together. That's a useful everyday image for what happens on a cosmic scale. Once the two black holes get close enough, they form a bound pair spinning around one another, and the challenge becomes how to get rid of more energy so the orbit tightens. Stars that pass too close act like billiard balls, getting flung out and carrying away orbital energy. Gas can form a disk and act like a viscous fluid, draining energy as it swirls around, much like oil slowing down two gears rubbing together. Observationally, astronomers sometimes see two bright centers in one merging galaxy, called dual-active galactic nuclei, which is a clear sign both black holes are actively feeding on gas. Think of it as spotting two headlamps in a foggy street instead of one. As the pair tightens further, exotic outcomes become possible. Three-way encounters can happen if another galaxy brings in a third black hole, and the interactions often kick one object out at high speed, in the same way a door slamming in a crowded hallway might send someone tumbling aside. When the orbit finally shrinks enough that gravity itself carries away energy in the form of ripples through space, gravitational waves, the two black holes sweep together in a dramatic finale. These ripples are like the tremors felt when a truck drives across a wooden bridge. They reach telescopes and timing arrays tuned to very low frequencies, and future space-based detectors are designed specifically to catch such heavyweight mergers. The consequences of these collisions shape galaxies in practical ways. Gas driven inward by the merger can fuel bursts of star formation and feed the black holes, lighting up the center with activity and sometimes producing bright flares when the gas is disturbed. The merged black hole often sits heavier and can spin faster, which affects how it interacts with its surroundings afterward. In a few cases the merged remnant can be kicked far from the galactic center, wandering like an unlucky tourist who took a wrong turn. All of this matters because these interactions help explain why some galaxies have quiet centers while others blaze with energetic outflows. In everyday terms, mergers rewrite the neighborhood plan, sometimes gently, sometimes like a demolition crew with taste. Hierarchical growth. Building mass over cosmic time. Supermassive black holes grow by two main, observable routes, pulling in gas and dust that surround them, and merging with other black holes when their host galaxies collide. Gas spirals in, forming a bright, hot disk as it falls. That glowing disk is what astronomers call an active galactic nucleus or quasar, which can outshine the whole galaxy while the black hole is feeding. When galaxies meet, their central black holes are carried along in the wreckage and can pair up, then sink toward the newly formed center and eventually coalesce, adding their masses together. The process of sinking toward the center is helped by a kind of cosmic friction. Stars and gas act like a thick crowd that tugs on the wandering black holes, stealing away orbital energy so the pair gets closer. This is similar to how a runner slows down when pushing through a dense crowd. Over time, the pair loses momentum and moves inward. At small separations, the pair can continue to zero in by interacting with surrounding stars or gas, and finally by emitting ripples in spacetime called gravitational waves that carry away the last bits of energy. Those ripples are very faint but real, and they are the universe's way of rounding off the merger. Feeding from gas is not limitless. There is a natural cap where the light and heat produced by the falling material push back on the inflow, slowing down the meal. Think of it like trying to pour syrup into a teacup while steam blows outward from the cup. At some point the outward push stops more syrup from falling in. This self-limiting behavior means black holes often grow in spurts, a hungry, messy binge when lots of gas is available, followed by quieter stretches when the surroundings are depleted or heated. That heating and pushing of gas by the accreting black hole, called feedback, can regulate both the black hole's growth and the galaxy's ability to form new stars. In everyday terms, it's like a parent who eats all the snacks and then turns off the kitchen light so no one else can raid the cupboard. The hierarchical picture means structures build up from small to large through repeated mergers. Small black holes and smaller galaxies merge and, over many such events, form more massive central black holes inside bigger galaxies. Simulations of the universe that follow how matter piles up and collides show this bottom-up assembly naturally emerges, and observations support it. The biggest black holes tend to live in the centers of the largest galaxies, and there are empirical links between a galaxy's central bulge and the mass of its black hole. Those links are useful because they tell us the two grew together, like business partners whose fortunes rise and fall together. Environment and timing matter a lot. Dense regions with lots of gas and frequent galaxy encounters are fertile ground for rapid growth, while isolated galaxies with little gas provide fewer opportunities. Sometimes a merger leaves one black hole wandering away from the center for a long time, like a CEO getting lost after a corporate reshuffle. Other times, gas-rich collisions funnel fuel efficiently to the core and trigger luminous quasar phases. Observations across many galaxies show a wide variety of growth histories, which is why astronomers combine surveys, simulations, and gravitational wave searches to piece together the full story. In short, supermassive black holes bulk up through repeated meals and mergers, with the local neighborhood and the physics of radiation and gravity setting the pace. It's a slow and messy form of construction, more like stacking boulders than assembling Lego, and it leaves behind signatures, bright outbursts, merged remnants, and correlations with galaxy properties that help scientists read the cosmic record. A little chaotic, a little elegant, and occasionally dramatic enough to make the universe's tabloids. Feedback: how black holes shape their host galaxies. Supermassive black holes release enormous amounts of energy as gas falls into them, and that energy changes the gas and stars around the galaxy. Gas spirals inward like water down a drain, forming a bright disk that can shine more brightly than the whole galaxy. This light and the fast-moving matter near the black hole push on surrounding gas and can fling some of it away. There are two easy-to-understand ways this happens: bright radiation that heats and pushes gas, and narrow, fast jets that slam into the galaxy's atmosphere. Think of it as the galaxy having a tiny but extremely powerful heater and a pair of high-pressure garden hoses, both able to move and change the environment. Radiation-driven winds act like a powerful fan or hairdryer aimed at a pile of leaves, blowing them outward and stopping them from piling up again. In real galaxies, these winds show up as fast-moving gas seen in telescope spectra, and observers have also measured cold molecular gas being carried away in these outflows with instruments like ALMA. When cold gas, the raw material for making stars, is heated or removed, star formation slows or stops. That's how a bright, growing black hole can turn off the galaxy's star factory. A little cosmic humor is unavoidable. It's like a very grouchy chef blowing out the steam so no more soup can simmer. Jets are more mechanical and focused. They look like tight beams shooting out from the black hole's poles, punching holes and inflating bubbles in the hot gas that surrounds galaxies and even galaxy clusters. 10th ray maps often show cavities where the jets have pushed the hot gas aside, and radio images trace the jet material itself. Those cavities act like an insulating blanket or a kettle lid that keeps gas from cooling and condensing into stars, so the galaxy can't keep feeding a steady supply of new stars. In some cases the jets are obvious, such as the dramatic one seen from the giant galaxy at the center of a nearby cluster. It's a clear sign that a small region around the black hole is controlling the fate of gas on much larger scales. Not all effects are purely destructive. Sometimes the pressure from a jet or a wind compresses a dense cloud of gas just enough to trigger a small burst of star formation, like squeezing a sponge and forcing out a little water in unexpected places. Observers have found pockets of new stars where jets hit dense gas, showing that black hole activity can both stifle and spark star birth. More often, though, feedback acts as a regulator. Black hole outbursts happen in bursts, not continuously, so a galaxy goes through cycles of feeding and fasting. This flickering maintains a balance. If the galaxy gets too full of cold gas and stars start forming too fast, the black hole can respond and rein things in. On the largest scale, this self-regulation helps explain why many big galaxies end up gas-poor and quiet, while smaller ones remain active, and why the mass of the central black hole is linked to properties of the galaxy around it. Black hole feedback ties a tiny region near the event horizon to the whole galaxy's evolution, like a thermostat keeping a house from overheating. Scientists combine many kinds of observations: 10th ray cavities, fast winds in spectra, radio lobes, and maps of cold gas, to piece together this story. So while a supermassive black hole may seem like a distant oddity, its behavior is essential for shaping the galaxies we see, and sometimes it does so with the subtlety of a gentle push and other times with the gusto of a cosmic sneeze. The M-sigma relation, a cosmic conversation. In many galaxies, the mass of the central black hole tracks how fast the stars in the galaxy's central bulge are moving around. Those star speeds are not about a single circular orbit but about how much the stars jitter and swirl in different directions. Astronomers call that jitter velocity dispersion, which you can think of as how frantically people shuffle in a crowded subway car. This link between black hole mass and stellar jitter is surprisingly tight across a wide range of galaxies, which tells us the black hole and the surrounding stars are not independent neighbors but are, in a sense, talking to each other. Measuring each side of that conversation uses different tools. To get the star jitter, observers look at the galaxy's light and see spectral lines broaden. Essentially, the starlight is Doppler shifted by many stars moving at different speeds along the line of sight, and that broadening tells you how chaotic the motions are. To estimate the black hole's mass, astronomers watch how stars or gas close to the center move under the black hole's pull, or they use special techniques like tracking very bright, variable light from the center to infer distances and speeds. In rare cases, natural radio beacons known as masers give a very precise measurement. If direct measurements aren't possible, the tight relation between mass and jitter becomes a practical shortcut to guess the black hole mass from the bulge properties. There are a few ways to explain why this relation exists, and none of them are as simple as saying, the black hole tells the galaxy what to do. One popular idea is feedback. As the black hole grows, it can eject energy or push gas out of the central region, and that can slow or speed up star formation and change how stars move. Another idea is shared supply. Both the central black hole and the bulge grow from the same reservoir of gas during events like mergers, so they end up correlated simply because they fed from the same pantry. Think of it like a town square and its mayor. Sometimes the mayor sets the rules, sometimes the town's mood influences who becomes mayor, and sometimes both are shaped by a big annual festival that provides most of the food. The relation is useful but not absolute. Astronomers use it to estimate black hole masses when direct dynamical measurements are too hard, and it helps calibrate simulations of galaxy formation. Yet not every galaxy follows the rule perfectly. Systems with unusual histories, or those that lack a classic bulge of stars, can be outliers. Active galaxies that are currently feeding strongly sometimes show more scatter, as if the conversation has gotten louder and messier. The takeaway is practical. The relation is a powerful tool, but like any rule of thumb, it works better in some situations than others. At the heart of it, the M-sigma relation feels like a cosmic conversation in which both speakers influence the tone. The black hole's mass and the bulge's stellar motions are intertwined through feeding, feedback, and shared history. It's a conversation researchers are still eavesdropping on, refining the translation, and occasionally laughing at a surprising aside, like finding a galaxy where the black hole behaves like a shy neighbor who nevertheless controls the streetlights. Spin and energy, how black holes twist space. Many supermassive black holes spin, and that rotation carries a huge store of energy that affects everything nearby. When an object rotates, it drags the space around it a little bit, and around a black hole this effect is extreme. Space itself is twisted in the direction of the spin, so that anything close in must move with the swirl. Think of it like a supercharged carousel. If you stand near the edge, you are forced to go around even if you try to stand still. That forced motion is a real physical effect, not just a metaphor, and it changes how matter and light behave close to the hole. Close to a spinning black hole there is a zone where the twisting is so strong that no object can remain stationary relative to distant space. This region, outside the point of no return, acts like a treadmill that is moving under your feet. A useful everyday image is a moving walkway at an airport. If the walkway is faster than you can walk, you have to move with it. In the black hole case, particles and light can gain or lose energy in this region depending on how they interact with the moving space. One practical outcome is that some processes can tap the black hole's rotational energy and send it outward, instead of letting everything fall in. Magnetic fields play the role of extraction tools in many black hole systems. Gas falling toward the hole often carries magnetic fields with it, and those fields can twist and knot as the hole spins. The result is a powerful mechanism that converts rotational energy into streams of particles and radiation that shoot away from the poles. We see these as narrow, bright jets. A helpful everyday comparison is a wind turbine. Wind moves the blades turn a generator, and electricity flows out. Here the spinning black hole is the moving part and magnetic fields are the generator that channels energy into the jets. It's both elegant and a little like using a cosmic blender to make a galaxy-sized smoothie. Astronomers infer how fast a black hole spins by observing the light from the inner disk and the behavior of jets. The inner disk's glow is affected by how close gas can orbit before plunging in. A faster spin allows stable orbits nearer the hole, so more gravitational energy is released as light. Observations of 10th ray signatures and the shape and power of jets give clues to that spin. In simple terms, the closer the light-emitting gas gets to the hole without falling in, the more efficiently the system can shine, like being able to take advantage of steeper drops on a waterslide to gain more speed. Spin also influences the environment on larger scales. When energy is extracted and launched outward, it can heat or push away surrounding gas and dust, altering star formation in the host galaxy. That feedback loop helps explain why some galaxies are bright and active while others are quiet. A playful comparison is that a spinning black hole can act like a very fussy thermostat for its galaxy, turning up or down the heating depending on how much rotational energy is put to work. Overall, the spin of a supermassive black hole is not just a detail, it is a reservoir of usable energy and a mechanism that twists space, drives powerful outflows, and shapes the surroundings. The physics can be described with analogies anyone recognizes: carousels, turbines, and moving walkways, and yet the results are spectacular: focused jets, energetic light, and a profound alteration of the nearby fabric of space itself. It's cosmic machinery with a touch of everyday practicality and a wink of humor, all powered by rotation. Gravitational waves, listening to black hole mergers. Gravitational waves are ripples in the fabric of space itself, produced when massive objects accelerate, and collisions of black holes make some of the loudest ripples we can hope to hear. They travel outward at the speed of light, carrying information about the motion and mass of the objects that made them. Think of the effect as a pebble thrown into a pond. The water ripples outward and the pattern of those ripples tells you about the pebble's size and how it hit the surface. In the cosmic version, the pond is space and the pebble is a pair of black holes spiraling together. To pick up these tiny shifts we use laser interferometers, long arms with laser beams that bounce back and forth, comparing the length of each arm to a precision so fine it can detect changes far smaller than an atom. Detectors on Earth such as LIGO and Virgo, joined by others like CAGRA, act together like a set of ears. Differences in the times and shapes of the arriving waves allow scientists to figure out where on the sky the signal came from. It's a bit like identifying which window a car alarm came from by listening from several spots in a neighborhood. The signals themselves often arrive as a chirp, a rising tone as the two black holes spiral faster and finally collide. That chirp carries the fingerprints of the masses and how fast they were spinning, all encoded in the rise and fall of amplitude and pitch. Listening is not easy. The waves that reach Earth are extremely weak and buried in a noisy background from terrestrial vibrations and instrument hiss. Researchers use advanced data analysis, filtering, pattern matching, and statistical tests, to pull real signals out of that noise, much like isolating a single violin in a busy orchestra. From the cleaned-up waveform we can estimate how heavy the black holes were and whether they were spinning in the same direction or wildly tilted, which in turn helps distinguish formation scenarios. For a familiar comparison, hearing the cadence and force of footsteps can tell you whether a visitor is a jogger or someone wearing heavy boots, even if you never see them. Future space-based listening posts will open a different part of the gravitational wave spectrum, tuned to the deep, slow bass notes produced by much more massive black holes merging. Where ground instruments hear the quick chirps of smaller mergers, a space observatory will hear long, low tones that unfold over long stretches of time, revealing collisions of giants that shape galaxies. Combining gravitational wave sound with light from telescopes, when available, gives a fuller picture, similar to watching a thunderstorm while listening to the thunder to judge distance and strength. Black holes themselves don't shine, so their gravitational music is the best way to study them up close. They may be terrible at taking selfies, but they are excellent at sending cosmic ripples that let us listen in and learn. Observing the invisible, multi-wavelength astronomy. Black holes themselves do not shine in ordinary light, so astronomers must use many kinds of light to study them. Light comes in many colors, beyond what our eyes can see, from long radio waves to very short gamma rays, and each kind carries different information. Think of it as using different camera filters and sensors to inspect something you can't touch. Each filter shows a different detail. Radio waves often reveal huge jets and the broader structure around a black hole, because these long wavelengths trace clouds of charged particles moving at high speed. Infrared light shines through dust and shows the warm glow of gas and stars near the center of a galaxy. Visible light can show starlight from the galaxy itself and sometimes bright gas that has been lit up by the black hole. Ultraviolet points to very hot gas, and 10th rays and gamma rays come from the most extreme, energetic processes right near the black hole's feeding zone. An everyday comparison, using a thermal camera to spot heat leaks in a wall, while a regular camera shows paint color and a metal detector finds hidden nails, each tool finds something the others miss. Telescopes on the ground and in space are tuned to these different kinds of light. Combining many radio dishes together makes a much sharper view, similar to using many small mirrors to create one giant mirror. Space observatories avoid the blurring effects of our atmosphere and catch ultraviolet and 10th rays that never reach the ground. Dust often hides the central region's invisible light, but infrared can slip through like a flashlight beam through fog. That's why astronomers switch wavelengths the way a mechanic switches tools. If one tool can't reach, another will. Timing is also important. Rapid flickers of light in 10th rays or optical bands often mean the source is very compact, so watching how the light changes tells us about size and motion. Putting all of these observations together is like building a medical diagnosis for a galaxy. 10th ray scans, infrared checks, and radio images combine to reveal how the black hole is feeding and how it's affecting its surroundings. Practical outcomes include estimating how fast a black hole is growing and how its outflows push gas away and shape star formation. It's detective work with cosmic clues, and sometimes the universe rewards patience with a surprising twist. Every wavelength fills in a piece of the puzzle, and the final picture is far richer than any single view. In the end, studying black holes across the spectrum is a bit like cooking a complex dish. You need multiple ingredients, and skipping one changes the flavor. Astronomers mix and match the light to taste the true nature of these hidden giants, and they keep refining the recipe with better instruments and smarter analysis, with occasional moments of triumph and a few burned soufflés along the way. The Event Horizon Telescope, imaging the abyss. A global network of radio telescopes is tied together to act like one enormous eye, large enough in effect to see the outline of the darkest objects in the universe. The event horizon, the edge beyond which nothing, not even light, can escape, is what these observations aim to reveal, seen as a dark shadow against a ring of glowing gas. Think of the ring as brake lights on a car. The bright glow tells you where stuff is moving and how fast, and the dark center tells you where light disappears. Simple words make the idea easier. The telescopes don't look at the black hole directly, they map the glow of hot gas swirling just outside the point of no return. By using a technique that links telescopes spread across the globe, astronomers increase the effective size of their dish without building one that big. Each site records radio waves from the same source at the same time, using extremely precise clocks to stamp the data so everything lines up later. Combining the recordings is like stitching thousands of smartphone photos into a single panoramic shot, but vastly more complicated and with much more math. The atmosphere interferes with the signal, so observers must correct for blinking and fuzziness caused by air and weather. It's similar to cleaning a fogged-up camera lens before taking a close-up. Because only certain pairings of telescopes sample specific pieces of the wave pattern, the data end up patchy and uneven. Reconstruction algorithms fill in the gaps, borrowing patterns and physical rules to build a coherent image from incomplete information. Picture trying to assemble a jigsaw puzzle with many missing pieces, but knowing the picture should look roughly like a glowing donut, that prior knowledge helps guide the fit. These computational methods also weed out noise and flare-ups from the instruments themselves, and they let scientists test different assumptions about how gas behaves near extreme gravity. The result is not a single raw photograph but a carefully made image, an interpretation grounded in physics. The practical payoff goes beyond a striking picture. Movies and simulations of the flow of matter around the hole gain real-world checks, and theories about how gravity works in the most intense conditions face direct tests against the observed silhouette. Imaging techniques developed for these projects spill over into other fields, too: medical imaging, wireless sensing, and even better ways to combine data from distributed sensors. And yes, there's a little cosmic theater involved. Scientists peer at what was thought invisible, like trying to see the shadow of a tiny insect on a distant wall. It makes a fascinating blend of clever engineering, patient data work, and a touch of poetic surprise. Simulations and supercomputers, virtual universes. Supercomputers recreate the physics of whole galaxies and the growth of giant black holes by solving the same basic rules that govern motion, gas flow, and light, but at a massive scale. They do this with software packages such as Illustris, Eagle, Aripo, and Gadget, which act like recipe books telling the machine how matter should move, cool, clump, and sometimes explode. Instead of stirring batter by hand, the code follows equations for gravity and how gas behaves, stepping forward in tiny increments and letting structures form naturally from the initial conditions. Observations from telescopes are then used to check whether the virtual galaxies look and behave like the real ones. Computers running these codes are not ordinary desktops. They use many processors and graphics units working in parallel so large problems can be split into smaller ones and solved together. Think of a team of cooks each handling a different part of a big banquet instead of one person trying to cook everything alone. The more processors you bring in, the finer the detail you can afford. You can see smaller clumps of gas and the paths of individual streams falling into a black hole, but the price is steep. The work grows quickly and needs lots of computing time. Visual outputs from these runs are often turned into colorful movies and images that look like art, and they help scientists spot mismatches between models and the sky. Not every physical process can be followed down to the tiniest scale, so simulations use simplified recipes, called subgrid models, for what happens below the code's resolution. It's like baking: you do not track every molecule of yeast, but you put in rules for how dough rises. For black holes, those rules describe how they swallow nearby gas and how some of that energy pushes the surrounding gas out, which can shut down star formation. These feedback recipes are tuned so that the collective behavior of many simulated galaxies reproduces observed trends, such as bigger galaxies tending to host bigger central black holes, even though the tiny details are not resolved directly. Simulations are practical tools, not just pretty pictures. They help interpret telescope data, suggest what new instruments should look for, and predict signals from events like black hole mergers that observatories might catch. They also expose blind spots. When a virtual universe fails to match reality, it tells researchers that some physics is missing or misrepresented, which is a useful kind of failure. And yes, running one of these simulations can be a bit like giving the cosmos a sandbox and a very expensive shovel: messy, educational, and occasionally satisfying when a spiral galaxy forms just right. Chemical enrichment, black holes and cosmic metals. Black holes influence the chemical makeup of galaxies by pushing around gas that already contains elements made in stars. Stars are the factories that build heavier elements, what astronomers call metals, and when those stars explode or die they release those metals into the surrounding gas. Active black holes, especially when they are fed lots of gas, launch strong winds and narrow jets that shove that enriched gas outward. This process doesn't create new metals, rather it redistributes them across a galaxy and even into the space between galaxies. Observations show evidence of this redistribution. 10th-ray telescopes reveal iron and other elements in the hot gas-filling galaxy clusters, and the pattern of those elements often points back to energy input from a central active black hole. Quasar light, when split into a spectrum, displays lines from carbon, nitrogen and other metals close to the bright black hole region, indicating that heavy elements are present even near these extreme objects. These measurements help astronomers trace where metals are concentrated and where they have been carried by winds or jets. A simple analogy helps. Think of a pot of vegetable soup that has pieces of carrot and potato at the bottom. If you stir it vigorously, those bits mix throughout the whole pot. Black hole outflows are the cosmic spoon. Sometimes the stirring is gentle and metals stay near the galaxy center. Other times the black hole acts like a leaf blower, launching material far into the galaxy halo and beyond. This movement matters for later star formation because if the metal-rich gas is removed or heated, fewer new stars form in the central regions, and the composition of future stars changes. Black hole-driven enrichment also affects the space between galaxies, known as the intergalactic medium. Astronomers find metals in regions too far from galaxies to have gotten there only by star explosions, so winds and jets are the likely transporters. In clusters of galaxies, bubbles blown by black hole activity can uplift metal-rich gas from the central galaxy and spread it through the cluster. That redistribution shapes where cooling gas can condense into new stars, and therefore alters the chemical evolution of entire galaxy populations. On a human scale, it's a bit like wildfire smoke carrying soot across a city. The source doesn't create new soot mid-air, but it spreads what exists to new neighborhoods. Black holes can be messy neighbors. They can both quench and trigger star formation by moving and heating gas, and so the pattern of metals we see today is a combined fingerprint of many cycles of stellar production and black hole stirring. A little cosmic humor: these monsters do not eat and sprout gold coins, but they are excellent at scattering the treasures that stars already made. Dark matter and black hole formation, friends or foes? Dark matter is the invisible stuff that makes up most of the gravity in and around galaxies, a conclusion drawn from how stars orbit and from light bending around massive objects. It does not emit or absorb light, so astronomers infer its presence from effects like galaxy rotation speeds and gravitational lensing. Black holes, by contrast, are regions where gravity has pulled matter so tightly that not even light escapes, and the biggest ones sit at galaxy centers and power bright objects called quasars. One clear way dark matter helps black holes form is by acting as a gravitational scaffold. Dark matter gathers into large, diffuse clumps called halos, and those halos create deep wells of gravity that pull in ordinary gas. Think of the dark matter halo like a valley that channels rainwater toward a central puddle. Gas flows down and can collapse into stars and sometimes into a compact seed that will grow into a black hole. Computer simulations that include dark matter and gas show that this funneling effect makes it much easier for dense pockets to form in galaxy centers, where black holes can begin their life. But dark matter can also be limiting, because it behaves differently from the gas that actually makes black holes. Ordinary gas can cool by radiating heat and thus collapse to very high densities. Dark matter, in most theories, does not cool or collide much, so it cannot simply clump into a tiny point and turn into a black hole on its own. Picture a crowd of invisible people who refuse to hold hands. They can shape the room by where they stand, but they won't huddle into a tight knot. That's why dark matter is generally seen as an indirect partner. It sets the stage but doesn't walk onto it. Some alternative ideas give dark matter a more active role. If a form of dark matter were sticky or could lose energy, what scientists call self-interacting or dissipative dark matter, then it might clump more strongly and even help form compact objects. These versions are speculative and are tested against observations. Another proposal suggests some black holes might be primordial, born from early universe conditions rather than from stars, and those primordial black holes could in principle make up some dark matter. Observations place limits on how much of the dark stuff could be in that form, though, so it is not the mainstream explanation. Astronomers use several practical tools to untangle these relationships. Observations of distant bright quasars and the shape of galaxies provide clues about how quickly black holes grew and whether dark matter halos were efficient at funneling gas. Gravitational waves from black hole mergers give an independent handle on how black hole populations evolve. And huge computer simulations let researchers change the assumed behavior of dark matter to see what happens. It's a lot like running traffic models for a city when you tweak how drivers behave. Each new observation narrows the range of possibilities. In short, dark matter is mostly a friend to black hole formation, but in a passive, shepherding way. It pulls material inward and creates the conditions where black hole seeds can form, but it generally cannot collapse itself into those seeds. Whether it could ever be a direct maker of black holes depends on properties we have not yet confirmed. So until dark matter starts paying utility bills or learning to radiate like ordinary gas, it's more of an invisible architect than a bricklayer, helpful, but not doing all the heavy lifting. Supermassive black holes in dwarf galaxies, surprising habitats. Astronomers have found that huge black holes can live inside very small galaxies, and that blew a few expectations. Small galaxies, often called dwarf galaxies, were thought to be too tiny and calm to host such massive beasts, yet objects like RGG 118, NGC 4395, POX 52, and Haineis 210 show clear signs of central black holes. These are not the monstrous giants at the centers of big galaxies, but they are still noticeable because they make tenth rays, radio waves, or cause nearby stars and gas to move in odd ways. In plain words, even small towns can have a big troublemaker in the middle of town hall, and astronomers can spot the commotion. Detecting these hidden giants uses different tricks. Telescopes that see tenth rays and radio waves often pick up energetic light from gas as it gets heated and pulled toward a black hole, like a pot that starts to hiss when the burner is on. Sometimes scientists watch how stars or gas swirl around the center. If they orbit very fast, something heavy must be pulling them. Other times the galaxy shows bright emission lines in its spectrum, which is like a fingerprint left by gas that got excited. Each method has its limits, and combining them gives the clearest picture, much like asking several neighbors about a strange noise rather than trusting just one account. How these black holes got into small galaxies is still a lively question, and there are a few reasonable ideas. One idea says small seeds formed early and then slowly grew by eating gas or by swallowing other smaller black holes. Another idea proposes that crowded star clusters collapsed to form a single, heavier object that later became a black hole. A third possibility is that gas in some places collapsed directly into a compact object without needing many steps. Think of it like baking. Sometimes you start with a tiny seed and let it rise slowly, sometimes you collapse a whole loaf into a roll quickly. None of these scenarios is proven for every case, and different dwarfs may have different stories. Finding black holes in dwarf galaxies matters for more than curiosity. These small systems can show how black holes affect their homes when the gravity and gas are weak, and the consequences are dramatic. A relatively modest black hole can blow wind and heat up the surrounding gas, slowing or stopping new stars from forming, like a strong heater drying out the soil in a small garden. Because dwarf galaxies are simpler than big ones, they act like convenient test labs where astronomers can tease apart cause and effect. Better telescopes and deeper surveys are now turning up more of these surprising habitats, so expect more strange neighbors to be revealed. It turns out the universe puts big surprises in small packages, and sometimes with a wink. Quenching star formation, the quieting power of AGN. The bright, energetic core of a galaxy can change how and where stars form by injecting energy into the surrounding gas. Cold gas is the basic raw material for making stars. It needs to be dense and calm enough to collapse under gravity. When an active galactic nucleus, a very energetic central engine powered by a supermassive black hole, puts out large amounts of light, heat, or fast-moving material, that fuel gets warmed, stirred, or pushed away, and the star-making process slows or stops. Radiation from the core can heat the gas so it can't cool down and clump. Think of trying to bake bread in a kitchen where someone keeps blasting a heater. The dough never chills and behave to rise properly. Sometimes the AGN launches narrow jets of material or broad winds that act like powerful garden hoses aimed through the gas, clearing out the fuel for new stars. Observations back this up. Astronomers see bright jets coming from certain galaxy centers and cavities in hot gas around them, clear signs that energy has been injected and gas has been displaced. The ways the central engine quiets star formation are varied. One route is heating. Light and energetic particles warm the gas, raising its pressure until it resists collapse. Another is mechanical removal, where outflows physically push gas out of the star-forming regions, much like a strong fan blowing leaves off a lawn. Additionally, the turbulence stirred by these processes can keep gas mixed and scattered instead of letting it settle into dense clumps. Turbulent gas is a poor nursery for stars. Each of these effects alone can slow star formation, and together they are even more effective. Real galaxies show the aftermath. In some systems, messy trails of fast-moving gas are seen streaming away from the center. In others, the surrounding hot gas displays bubble-like cavities where jets have punched through, similar to how a canoe paddle leaves gaps in a calm pond. The overall result is that once the central engine has done its job, the galaxy's star-forming regions grow quieter, with less cold gas available and fewer newborn stars. It's a bit like a neighborhood coffee shop turning off its ovens, fewer fresh pastries on the counter, and people stop gathering for breakfast. Duty cycles, when black holes sleep and wake. Supermassive black holes at the centers of galaxies do not shine all the time, they switch between hungry, bright phases and quiet, faint ones. The bright phases occur when gas and dust fall toward the hole and form a hot, glowing disk that lights up across many wavelengths, from radio waves to 10th rays. In simple words, accretion is the process of matter spiraling in and heating up, and that heated matter is what makes a black hole awake or active. Our own galaxy hosts a central black hole that is mostly quiet now, though it occasionally flares, which shows that sleeping and waking can happen on many scales. Fuel availability determines the schedule. If a galaxy funnels fresh gas inward, through a crash with another galaxy, a wobble in its own disk, or the slow shedding of gas from dying stars, the black hole gets a meal and brightens. If there's no fuel, it goes dim. You can think of it like a campfire that flares when someone adds logs and smolders when the pile runs out. Sometimes the black hole's own energetic output blows the nearby gas away, shutting off its food supply and forcing it back into a nap. That self-regulation is a kind of cosmic appetite control. Astronomers piece together how often black holes are active by looking at large samples of galaxies and by finding the remnants of past activity. Surveys that count how many galaxies show bright centers give a kind of snapshot estimate of duty cycles, while fossil radio lobes or glowing gas clouds act like archaeological evidence of earlier feasts. It's a bit like going down a street at night. If many houses have lights on, you infer that people are awake, but if only a few glow, you infer most are asleep. Short-term flickers and long-term changes both matter. Light variations can be seen over short stretches, and signatures of past outbursts can linger for a long time. Understanding these on-off patterns matters because the wakeful periods can heat or push away the gas that would otherwise make new stars, changing the whole galaxy's life story. Active phases can carve bubbles, drive winds, and reshape where new stars form. In practical terms, learning how often and why black holes wake up helps astronomers predict how galaxies grow and why some are full of young stars while others seem old and quiet. And for those who like cosmic metaphors, black holes are picky eaters with unpredictable sleep schedules, noisy neighbors when fed, blissfully silent when not. High-redshift quasars, monsters in the young universe. Quasars seen at great distances act like cosmic beacons, throwing out enormous amounts of light from the centers of young galaxies. They are powered by supermassive black holes so heavy they weigh millions to billions of times as much as the Sun, gorging on surrounding gas that heats up and shines. The light we receive from the most distant of these objects has been stretched by the expansion of space and shifted toward redder colors, which is what scientists call high redshift. In practical terms, that means the light started its journey when the universe was much younger and has traveled a very long way to reach us. Observers rely on the stretched light landing in infrared detectors, because those long wavelengths are the ones that survive the trip and tell us about conditions far back in cosmic history. The environment around these hungry black holes looks wild. Gas forms a bright spinning disk as it falls inward, and some of that gas is launched outward in fast jets that can reach far beyond the host galaxy. Think of the disk like water circling a drain, heated until it glows, while the jets are more like surprise garden hoses shooting out along the drain's axis. Astronomers see signs of this activity through spectroscopy, which splits the light into fingerprints that reveal what elements are present and how fast the gas is moving. Broad emission lines in the spectrum mean gas is whizzing around at thousands of kilometers per second. In plain English, that's extremely fast, comparable to a car race where all vehicles are supersonic, minus the toll booths. How these supermassive black holes grew so big so quickly is a puzzle that keeps scientists up at night, well, figuratively. Several realistic pathways are studied. Some black holes might have started from relatively heavy seeds, formed by the direct collapse of dense gas clouds. Others could have grown by merging with many smaller black holes or by swallowing gas in one long, greedy feast. Practical analogies help. A small snowball rolling down a steep hill can pick up so much snow that it becomes enormous, or a hungry person might gain weight quickly if every meal doubles in size. Observations help narrow the possibilities. For example, the presence of massive amounts of dust and metals in some quasar-host galaxies suggests fast, efficient star formation happened alongside black hole growth, because those heavy elements come from short-lived stars. Studying these distant quasars also teaches us about the larger cosmic setting. Their intense light can change the state of the gas in their surroundings, making it easier for ultraviolet radiation to ionize atoms, and that process affects how galaxies form and evolve nearby. For practical astronomy, finding high redshift quasars means peering in the infrared and using sensitive instruments, both in space and on the ground, plus careful data analysis to separate faint quasar light from foreground noise. It's like trying to spot a lighthouse beam through morning fog while standing on a distant hill. You need the right lens, patience, and a stubborn streak. And despite the mystery and the complexity, there's a bit of cosmic humor in knowing that these early universe monsters were just doing what black holes do best: eat, shine, and surprise the folks watching from billions of light years away. SMBH mass measurement techniques, weighing the unseeable. Astronomers infer the masses of supermassive black holes by watching how nearby stars, gas, or light behave under their gravity. That is the basic idea. You cannot put a black hole on a scale, but you can watch things dance around it and use those motions to calculate how heavy the unseen partner must be. Think of it like judging how strong the wind is by seeing how fast leaves swirl. The motion tells you about the force causing it. One of the most direct approaches is to measure the motions of stars near a galaxy's center. When stars orbit fast and close, the central object must be very massive. Observations of individual star orbits near the center of our own galaxy are a textbook example. By tracing their paths, astronomers get a clear handle on the gravitational pull acting on them. Gas can also be used. Rotating disks of emission line gas around a nucleus show Doppler shifts, which reveal rotation speeds. But caution is needed because gas can feel extra forces, like pressure or outflows, so its motion isn't always purely driven by gravity. Another technique uses natural astronomical lasers, called masers, where water molecules amplify microwave emission in a thin, rotating disk. These masers can trace a nearly perfect Keplerian rotation curve, meaning the orbital speed drops off with distance in the way gravity predicts, and that gives very precise masses. One famous galaxy with such a maser disk provides a textbook case of a clean geometric measurement. For more active black holes that flicker in brightness, astronomers use a method called reverberation mapping. Bright light from an inner region changes and the surrounding gas responds after a time delay, like an echo. Measuring that delay tells you the size of the region, and combining it with the gas speed, from line widths, gives a mass estimate. That technique is often calibrated to produce single-epoch masses from one spectrum and a luminosity, handy when repeated monitoring isn't possible. Radio imaging at very high resolution has given another route, directly imaging the silhouette, or shadow, of a black hole against its glowing surroundings. When you can measure the angular size of that shadow and know the distance to the galaxy, you get a geometric constraint on mass. This is a powerful, visual method that complements motion-based techniques. Meanwhile, a future frontier is listening for gravitational waves from pairs of supermassive black holes as they spiral together. Low-frequency gravitational wave observatories planned for space and networks of pulsars on Earth will, when sensitive enough, provide direct measurements of masses for merging giants, a very different kind of weighing scale. Every method has its caveats. Resolving tiny regions requires extremely sharp telescopes, and assumptions about geometry and motion introduce uncertainty. Sometimes astronomers must apply a scale factor to translate observed speeds and sizes into mass, which is essentially a carefully estimated fudge factor rooted in physics. Distance uncertainties, orientation of disks, and contaminating forces like radiation pressure can all bias results. That's why multiple techniques are often used on the same object to cross-check one another, like confirming a recipe by tasting it in different ways. And yes, weighing something invisible remains partly an art, partly a science, and a bit like trying to figure out how heavy a dog is by watching how the leash jerks, funny when you picture it, but surprisingly effective when you know what to look for. Tidal disruption events, meals that flash and fade. When a star drifts too close to the huge black hole at the center of a galaxy, the difference in gravity between the near side and the far side of the star becomes so strong that the star is pulled apart. This stretching force is the same basic idea behind ocean tides on Earth, only far more violent. Think of a marshmallow being tugged into long, sticky threads instead of the gentle rise and fall of seawater. Some of the shredded stellar material is flung outward and lost forever, while the rest falls inward and forms a glowing stream or disk. The sudden brightening that follows is what observers call a tidal disruption flare. The flash can be extremely luminous, shining in tenth rays, ultraviolet, and visible light, then fading over months or even a couple of years as the meal finishes digesting. Telescopes that watch large parts of the sky for changes catch most of these events. Ground surveys that look for sudden brightening in optical light, and space telescopes that monitor tenth rays and ultraviolet light, have both found clear examples. Assassin 14 Li is one such well-studied case that produced both tenth ray and radio signals, and another famous event showed a jet blasting out like a cosmic fire hose. These observations tell astronomers not only that a star was torn up, but also what kind of matter fell in, how fast it fell, and whether the black hole launched a jet, sort of like reading the crumbs after someone has raided a cookie jar. The brightness usually follows a steady decline that scientists can model, so the fading light becomes a tool for measuring the black hole's appetite. The physical process can be explained without heavy jargon. As the star breaks, gas streams collide and heat up, friction and compression turn kinetic energy into light, much like how rubbing your hands warms them. Some debris gains enough speed to escape, like pieces of a broken vase flying off the table, while the rest settles into a swirling structure around the black hole where conditions become hot and bright. Occasionally the system produces a narrow, fast jet of particles that lights up in radio waves, a dramatic side effect, like a pressure cooker releasing a sudden hiss. Not every disruption looks the same. Differences in the star's path, how close it came, and the black hole's properties make each event unique. For astronomers, these flashes are more than fireworks. They provide a rare way to study black holes that are otherwise quiet and invisible, and to estimate fundamental properties such as how massive the hole is and how it spins. Surveys that keep an eye on millions of galaxies make it more likely to catch these rare meals, and detailed follow-up across multiple wavelengths helps piece together the physics. Sometimes the observations match predictions, and sometimes they surprise researchers, which keeps the field lively, and gives black holes yet another excuse for being mysterious dinner guests. Recoils and wanderers, kicked black holes in space. When two black holes merge, the newly formed object can get a sudden shove because the ripples they send outward, gravitational waves, aren't always sent out perfectly evenly. Gravitational waves are just waves in the fabric of space, like the ripples you see on a pond after tossing in two stones at once, and if those ripples carry away more momentum one way than another, the leftover push sends the remnant black hole off-center. The strength of that shove can vary a lot, in different situations it can be as small as a few tens of kilometers per second or as large as several thousand kilometers per second, so whether the black hole stays put or becomes an interstellar wanderer depends on how fast it's kicked and how deep the galaxy's gravity well is. Small galaxies have much weaker gravity, measured in the tens to a few hundred kilometers per second for escape speeds, while the biggest galaxies can hold on to objects moving at several hundred to over 1,000 kilometers per second. A kicked black hole can do strange things to its neighborhood. Sometimes it's only nudged away from the center and then slowly settles back, wandering through the galaxy like a dog that got bored at the dinner table. Other times it has enough speed to leave the galaxy entirely. It may drag along a tight cluster of stars and some gas that were tightly bound to it. Think of a celebrity leaving a party with a few loyal friends and a valet, forming what astronomers call a compact star system around the moving black hole. Observationally, these wanderers can show up as active spots that don't line up with the galaxy's center, or as gas clouds whose light is shifted in wavelength because the black hole is racing away from the rest of the galaxy. Astronomers look for these signs by comparing where bright 10th rays or optical emission come from relative to the galaxy's center, and by checking whether broad gas emission lines are shifted in velocity relative to the stars. The consequences for galaxy life are practical and sometimes surprising. A supermassive black hole kicked out of the center won't be able to feed on the dense, central gas as efficiently, so its growth can be slowed and the usual feedback effects, winds and radiation that regulate star formation, get shifted or weakened. That can change how the central regions of a galaxy evolve later, allowing gas to form new stars where it might otherwise have been heated and driven away. In crowded environments, like when a third black hole comes into play, interactions can become complex and produce even larger kicks, which is like three bumper cars colliding and sending one of them off at a strange angle. Detection and study of these kicked black holes mix careful observation with theoretical modeling. Astronomers search for off-nuclear active galactic nuclei, for stars tightly bound to an unseen massive object, and for Doppler shifts in broad emission lines that reveal motion. Low-frequency gravitational wave observatories and networks that time pulsars also provide complementary information about the mergers that cause such kicks. Together, these tools let researchers test models and predict how common wandering black holes should be. It's a cosmic game of hide-and-seek, and sometimes the seeker leaves with a noticeable limp, or a trail of gas and stars, so the clues are often there if you know where to look. Cosmological implications: black holes as probes of the universe. Most big galaxies harbor a giant black hole at their center, and when that hole is actively gobbling gas it becomes a cosmic lighthouse. Bright beams and glowing disks of hot gas shine for millions of light years, making these objects, called quasars when they are very bright, visible across vast distances. This light carries fingerprints of everything it passed through on the way to us. Astronomers read those fingerprints to learn about the gas between galaxies, its composition, and how it moves. Think of it like a distant streetlight shining through fog, except the fog can tell you what it's made of and whether it's drifting toward or away from you. When quasar light crosses an intervening cloud of gas, some wavelengths are absorbed and show up as dark lines in the spectrum, revealing chemical elements and temperature. That technique is like holding a stained glass window up to a lamp and deducing which colors the glass blocks. From those clues we can map where gas sits, how much there is, and how enriched it is with elements forged inside stars. Massive objects in galaxy centers, including black holes, also bend and magnify light from farther sources. This gravitational lensing acts like a natural zoom lens and lets astronomers measure how mass is distributed in a galaxy or cluster, which in turn tells us about the invisible stuff, called dark matter, that dominates the mass budget. Gravitational waves from merging black holes are another practical probe, and they speak to us in a different language: ripples in spacetime. These ripples carry a direct measure of distance in the same way that a loud thunderclap gives a clue to how far away a storm is. Combining that distance with how stretched the light is by cosmic expansion gives an independent handle on how the universe grows. Observing the bright surroundings of a black hole at the same time provides the redshift, or the stretch factor, of the universe for that source, and together the measurements test expansion models without relying on traditional distance ladders. In short, The mergers act like cosmic measuring tapes and help calibrate the big-scale map of the cosmos. Telescopes that can resolve the area very close to a black hole let scientists test how gravity behaves under extreme conditions. Simple comparisons: does light bend and time slow the way our best theory predicts, become powerful checks on fundamental physics when the gravity is strong. Combining information from light, gravitational waves, and other messengers is like running multiple medical tests on a patient. Each gives different clues and together they form a clearer diagnosis. As we collect more of these diverse signals, black holes will keep serving as versatile probes, lighthouses, tide gauges, and ripples in a cosmic pond, all rolled into one slightly terrifying but incredibly useful tool. Future observatories: what we'll discover next. Next-generation observatories will let us study the neighborhoods around supermassive black holes with a clarity we simply did not have before. Space telescopes that see in infrared light can peer through dust like night vision goggles into the crowded centers of galaxies, while networks of radio dishes acting together can take pictures as sharp as a camera the size of a planet. Other instruments will listen for ripples in space itself, tiny vibrations that tell us when two enormous black holes are spiraling together, and 10th-ray telescopes will map the hottest gas and energetic flares near the point of no return, the event horizon. Together, these different tools act like a set of senses: sight, hearing, and touch for the universe. Imaging the immediate surroundings of a supermassive black hole will become routine in more galaxies than just the closest ones. Better resolution will show how gas swirls in, how bright clumps appear and vanish, and how jets of matter launch out at near-light speeds. It's like watching a whirlpool at the drain and seeing the leaves that get pulled in and the spray that shoots out. Only here the whirlpool can outshine a whole galaxy. By tracking how hot gas moves we can measure how fast a black hole spins, and spin turns out to matter because it helps determine whether a galaxy gets a calm wind or a powerful jet. That helps explain why some galaxies stop making stars while others keep forming them. Listening for gravitational waves from very massive black hole pairs will be a game changer for finding mergers that are otherwise hidden. Gravitational waves are ripples in space caused by massive objects moving quickly, similar to how a boat makes waves on a lake. Space-based detectors tuned to the low, bass notes of these ripples will catch the slow, deep-sounding mergers of supermassive black holes long before they collide, giving astronomers time to point telescopes and watch for any light show. Combining these wave detections with light and radio observations, a practice called multi-messenger astronomy, is like having both a siren and a camera for cosmic events. It makes the picture far more complete. New observatories will also let us study how black holes influence their larger homes, the galaxies around them. We will be able to trace how black hole outflows push gas away and either choke off star formation or, in some cases, compress gas and trigger new stars. Think of it like an urban planner studying traffic. If you know where the jams form and how the flow changes, you can redesign the roads. In the same way, better data will let theorists build more realistic models of galaxy growth and evolution. Practical benefits follow too, since the advanced data processing and imaging techniques developed for these observatories often find their way into medical imaging, environmental monitoring, and other areas on Earth. Finally, better observations near the event horizon will test the laws of gravity under extreme conditions. Simple phrases like, "nothing escapes," get tested in detail by watching how light bends and how matter behaves in these intense fields. While we don't expect miracles, we do expect surprises that refine our understanding, and maybe even a few puzzles that keep theorists up at night. Astronomers will be busy, and that's fine. After all, a little cosmic drama keeps the field lively and gives everyone great material for coffee break conversations. Outstanding mysteries, the biggest unanswered questions. Supermassive black holes sit at the centers of many galaxies and are puzzling because we still do not fully understand how they grew so massive and how they interact with their surroundings. One big question is where the first seeds that became these giants actually came from. Some seeds might be the leftovers of very massive stars that collapsed, while others could have formed when huge clouds of gas fell straight into a compact object without forming many stars first. A third idea is that dense clusters of stars can collapse together into a single heavy object. These scenarios are different in how big the initial seed would be and how much work the black hole has to do to reach the sizes we see today, so figuring out which path or mix of paths nature took matters a lot. Growth speed is another mystery, and the language scientists use for the tug-of-war involved is often the Eddington limit, a simple idea: light pushing outward can balance the gravity pulling gas inward. If a black hole shines too brightly while it feeds, the light can blow gas away and slow further growth. But some observations suggest that black holes, at least at times, may have cheated by gobbling gas faster than that limit would normally allow. Think of it like a bank account with limits on deposits. Normally you can only add so much money per day, but sometimes someone finds a way to wire in a huge sum overnight. Understanding whether rapid, short-lived feeding spurts or steady, slow accretion are responsible is key. The connection between black holes and their host galaxies raises more questions. There is a clear link: heavier central black holes tend to live in galaxies whose central stars move faster or are arranged in a denser bulge. This relationship is often called the M-sigma relation. It suggests some two-way conversation between black holes and galaxies, but the script of that conversation is missing. Do black holes tell galaxies when to stop making stars by blasting out energy and heating or expelling gas, or do galaxies simply hand over gas to their black holes when conditions are right and then evolve on their own? Practical examples help. If the black hole is a heater in a house, it can warm or overheat the rooms and change how people live there, but the layout of the house also determines how easy it is for that heater to reach every room. Spin is a subtle but important unknown. How fast a black hole spins changes how efficiently it converts falling gas into light and how powerful any jets of particles it launches can be. Measuring spin is hard, like judging how fast a top is spinning from across a football field. Astronomers use clues from 10th rays and the motion of gas near the hole, but results can be ambiguous. The difference matters because a high spin can make a black hole a very efficient radiator and produce strong jets that punch through the galaxy, while a slow spin might keep things more sedate. Mergers of galaxies bring two black holes together, yet it's unclear how often these pairs actually coalesce versus lingering in a slow dance for a very long time. Once two holes form a close pair, they must lose energy to get close enough for gravitational waves to finish the job. The processes that drain that energy, interactions with stars, gas, or other black holes, are complex and not fully quantified. Picture two people trying to hug in a crowded subway car. They keep bumping into others and may take a while to finally squeeze together. The search for intermediate mass black holes fills another niche of uncertainty. We know of small black holes formed from dying stars and the huge ones at galactic centers, but the middle sizes are scarce and hard to confirm. Some bright 10th ray sources and motions inside compact star clusters hint at their existence, but alternative explanations often remain plausible. Finding a clear example would be like locating a missing link in a family tree. It would help explain how small objects can grow into truly enormous ones. Observational limits themselves create puzzles. Dust, distance, and the tiny angular size of the regions near a black hole make direct study difficult. Telescopes working across radio, infrared, optical and 10th ray bands each reveal different parts of the story, but piecing those parts together is like assembling a puzzle with many missing pieces. New methods, including timing arrays of pulsars and space-based observatories sensitive to low-frequency gravitational waves, promise to open fresh windows, but translating new detections into clear answers will take time and careful interpretation. Finally, uncertainty about how often and how violently black holes influence star formation in their host galaxies persists. Feedback can both quench and trigger star formation, depending on how the energy couples to the surrounding gas. It's a nuanced relationship. Sometimes a blast clears gas and halts star birth, and sometimes a shock compresses gas and seeds new stars. The exact conditions and balance that lead to one outcome or the other remain open questions. In short, these big unknowns, seeds, growth rates, spins, mergers, intermediate masses, and feedback pathways, frame the lively and sometimes baffling frontier in our study of supermassive black holes. Science in pop culture: black holes on stage and screen. Black holes are regions of space where gravity pulls so hard that not even light can escape, and that simple fact is often the starting point when theater and movies bring them to life. Filmmakers and show creators lean on a few recognizable features: a dark center called the event horizon, the point of no return, a glowing ring of gas and dust known as an accretion disk, and the way light itself gets stretched and warped around the hole. To make those ideas visible on screen, artists borrow from real science. The way light bends around massive objects, for example, creates the dramatic warped ring visuals audiences expect, and planetarium-style visuals and the first radio telescope images of black hole shadows have given directors real reference points to copy or stylize. On screen, accuracy and spectacle often take turns sitting in the director's chair. Some films try hard to show the real physics. They consult actual scientists to portray effects like time slowing down near a massive object, and they use computer models that follow Einstein's equations to craft believable images. Other works treat black holes as magic doors, horror monsters, or shorthand for the unknown. Science fiction shows will use a black hole as a plot device to whisk characters through time or into alternate universes, which makes for exciting storytelling even if the physics is stretched. Movies that aim for a more realistic look often still simplify things so audiences can follow the story. After all, explaining gravitational time dilation is a lot harder than exploding a spaceship. Stage productions and live events approach black holes differently, because theater is built around human bodies, light, and sound rather than CGI. Directors use lighting rigs, fog, projections, and shadow play to suggest the pull of a black hole. A slow, circling spotlight and a rising rumble of sound can do more emotional work than a detailed simulation. Immersive experiences in planetariums and science centers mix storytelling with interactive visuals, letting viewers fly toward a simulated black hole with headphones and curved screens. That tactile, shared feel is useful for education. Comparing an accretion disk to a spinning whirlpool or a drain in the bathtub helps people picture the physics, and small theatrical tricks, like actors slowly stretching away from each other to hint at spaghettification, the stretching effect caused by strong gravity, make the concept stick. The cultural role of black holes on stage and screen is twofold: they spark curiosity and they provide metaphor. Black holes stand in for loss, obsession, and the unknown in plays and films, while at the same time giving teachers and presenters a vivid hook to explain real science. Practical outreach uses these pop culture tie-ins. Classroom VR apps let students approach a simulated black hole, planetarium shows translate equations into spectacular visuals, and science communicators borrow film imagery to explain things without getting bogged down in jargon. And yes, they also provide easy jokes. A black hole is great for dramatic tension, but terrible if you're trying to find your car keys. Citizen science and public engagement: join the hunt. Large surveys produce millions of images and streams of data that professional teams alone cannot scan in detail, so volunteers help spot the strange and the useful, and that directly advances our understanding of how supermassive black holes grow. A supermassive black hole is essentially a very heavy object at the center of a galaxy that pulls in gas and stars. When it eats a lot at once, the center can glow very brightly, and those bright signals are what many citizen projects ask people to find. Projects like Galaxy Zoo and Radio Galaxy Zoo let non-specialists classify galaxy shapes and radio structures, and that simple act of sorting can reveal signs of collisions, bright cores, or jets that point to a feeding black hole. One famous example is the discovery of a strange glowing cloud by a volunteer, which turned out to be a clue that a black hole had been energetic in the recent past. Volunteers can literally point scientists to things they would otherwise miss. Classifying images is only one way to help. People also tag patterns in brightness over time, flag odd radio blobs, and sort through glitchy signals in detectors. Think of it like helping a robot learn to sort fruits. Humans show a few thousand examples of ripe versus unripe, and the machine gets better. In astronomy, human labels train algorithms to find active galactic nuclei, the bright centers tied to black hole feeding, so that automated searches become faster and more reliable. There is even distributed computing, where your spare computer cycles can help sift through gravitational wave or radio data, much like offering your lawn mower to help with the neighborhood cleanup on a lazy Sunday. Joining in is straightforward and practical. Sign up on citizen science portals such as Zooniverse, pick a project that asks you to look at galaxy pictures or light curves, and follow the short tutorial. The tasks are designed to be intuitive and you will learn as you go. Amateur astronomers contribute too. Small optical telescopes and backyard photometry groups can monitor changes in a galaxy's brightness and feed that data to professional teams, a lot like neighborhood weather stations reporting rainfall to the local forecast group. Participate in project discussion boards, ask questions, and read the field guides provided. Experienced volunteers often share tips that improve everyone's classifications. Do the work carefully and the science benefits. Consistency matters more than speed. When you spot something unusual, say so. Researchers often follow up on volunteer finds, and contributors regularly receive acknowledgments or are invited into deeper collaborations. Learning a few basic signs of active centers, for example, unusual color, concentrated point-like brightness, or long jets seen in radio maps, boosts your usefulness, and it's also fun. Helping to find clues about how supermassive black holes grow may not make you famous overnight, but it does put you on the team that helps uncover how whole galaxies evolve, and that's a pretty neat line on a resume. So that's the life story of supermassive black holes in plain terms. They started small, grew by gulping gas and stars and sometimes by crashing into other black holes, and in the process they helped shape the galaxies around them. Think of them like cosmic drain plugs, sometimes quietly pulling in matter like a bathtub drain, sometimes slurping loudly during a feeding frenzy, and sometimes two drains collide and become one bigger drain. They don't eat because they're greedy in a moral sense, they just follow gravity, and their eating can push gas away or kickstart new star formation, like a neighborhood construction crew that can both knock down and build up houses. If any part surprised you, the early rapid growth, the giant mergers, or how these dark giants sculpt entire galaxies, tell us which bit made you go, whoa. Your curiosity is the reason we keep looking up and turning complicated ideas into stories anyone can enjoy. If you like this cosmic journey, give the video a thumbs up, subscribe, and tap the bell so you don't miss what's next. Coming soon, we'll show how astronomers actually photograph a black hole using many telescopes working together, and we'll ask the big question, do black holes help make galaxies, or mostly just wreck them? Share this with a friend who loves space, and first we'll see you in the next video. Same curiosity, bigger telescopes, and maybe more coffee for the science team.